Okay, folks, so you're very welcome here to Engineers Ireland, and on behalf of CUNY Architects and I3BT, the sponsors, we'd like to welcome you here, and the Project Management Society and the Young Engineers Society, who have also been involved in putting this event together. I suppose, in aid of Space Week, we've managed to get both international and national speakers of some very high class. I've heard some of them speak before, and I'm really looking forward to this event. Some housekeeping issues, I suppose. Fire exits, the door you walked in, and the door at the bottom here. There's no fire drills planned. I would say turn off your phones, but they do block you here anyway, so engineers have come up with a solution to to keep you quiet, I suppose. But our first speaker we have is Stuart Green, and since 1998, Stuart has been the remote sensing specialist in the Spatial Analysis Unit in Teagasc. So unlike the rest of the speakers here, Stuart is coming from the outside looking in, as in using the satellites to generate imagery that can be used in order to help with farmers with environmental decisions, and when they examine the details that they can provide, they can improve their crop growth. I was asking Stuart up front there to see how does it work, kind of getting from a farmer perspective. You wouldn't necessarily they're that technology savvy. How does that communication go through? And he said mainly by telephone. So I'll be interested to see how that communication is carried out. So look, without further ado, and in the interest of getting the best out of the speakers and having a Q&A session at the end, so we're going to save questions to the end. I'm going to introduce you to Stuart Green of Teagasc. Thank you.
Thanks. Hello, everyone. I'm Stuart. This satellite picture, it's a bit of a fraud. Okay, I put it up there when I saw the rest of the speakers, and I realised just sort of how spacey, sort of spacesuits, exploration, designing spaceships. I'm really going to be talking about them. Really. Using satellites and space technology to look where the cows are, to look what the cows are eating, to look at their environment. I won't get through without mentioning cow poo at some point in the things, all observed by space. Okay? And what we're looking at is a technology Earth observation. So satellites orbiting the Earth, looking down. Okay? So what's a satellite image? For today, we think of these Earth observation satellites as being big digital cameras in space, okay, and pointing straight down. The really secret high-tech space satellites, spy satellites, they'd be a few hundred kilometers up. The sort of satellites I use, 600-700 kilometers orbital altitude. They go around the Earth maybe every 70 minutes, every 75 minutes. And we have a lot of them now. 20 years ago, there was one, maybe two. And you had to pay for the data, and it cost a fortune, and you only got one chance to get it. Now we're surrounded by data. This building would have been imaged maybe a dozen times in the last week by different satellites, all freely available mostly, that you can get and work on. We'll talk about that at the end. Satellite images, think of them digital cameras, but they gather the data in bits. Okay? They break up the observed spectrum, the reflected sunlight, into sections, just like a normal camera does, but more sections. This is a little bit of the Shannon Estuary down there. There's a little tributary. So in Limerick. And this is the reflected blue light from an image taken a few days ago. We can see forests, we can see the little bit of a river, some marshland and so on. So if it's dark, very little blue light was reflected. If it's bright, a lot of blue light was reflected. If we look at the green component of the image, suddenly it's much, much brighter because vegetation is green. And most of Ireland, the Emerald Isle, is green. And it's green because it reflects more green light than red or the blue. In the process of photosynthesis, the blue and the red light are absorbed and transformed into energy and then emitted when it's gotten rid of. But the green light is reflected. Probably about 10%, maybe 10% of the light that falls on a leaf is reflected back up in the green component. And there's the red, much darker. Lots of the red light is absorbed. Okay. We combine these and we get a colour image. Okay. So that, if you were strapped to the bottom of the satellite in the few seconds before you were asphyxiated to death, this is what you'd see. Okay. If it was cloud-free. That's a cloud. That's the bane of our existence. Took ages to find a cloud-free image, which we'll see later on. Now, the great thing about the satellites is they don't just look in the colour part of the spectrum, in the observed part of the spectrum, the visible part that we live in and use. The spectrum is vast, okay? Going from very long radio waves all the way to gamma rays. It's all the same stuff. It's all radiation, electromagnetic radiation. We just live in this little bit, the visible part, from blue light at 400 nanometers to red light at 700 nanometers. The satellite can measure a wide range of wavelengths. We're not going to concern ourselves with all these. These colour bars just tell us where the satellite is recording data from. So we can go all the way from very short blue light, which is used to measure the scattering in the atmosphere, all the way to very long infrared or shortwave infrared data that's used to help us discriminate between ice and snow and clouds. But we are going to look at this band here, called the very near infrared. And that's what a very near infrared image looks like. Much brighter than any other images I've shown you. And this is because the structure of the leaf, not the colour, the structure of the leaf, the spongy mesosphale, has a certain structure so that more than 50% of the shortwave infrared light that falls on it is reflected back up. They're very bright. It's 5 times brighter in the shortwave infrared than it is even in the green. So if our eyes could see that part of the spectrum, we'd be a very bright environment we're living in indeed. And we can combine these components of an image in the satellite, in the software, to give us what we call a false colour. So here we've embedded this information on the shortwave infrared, the near infrared that we normally can't see. And now it allows us to look at more detail at the vegetation across this image. And fundamentally, this is what I spend my time looking at, is the vegetation as revealed in this reflected part of the spectrum that we normally can't see. So dark areas to the forestry, the ranges of pinks and reds, different levels of grassland, the cyan colour, this is bare soil, okay, where the vegetation has been taken away. And we can do lots of analysis of this, but the simplest one to do is to take the ratio of the reflected near-infrared light and the reflected red light. And this is called a vegetation index. If that vegetation index is 0, it means we've got no vegetation, like that bare field there. If it gets close to 1, we've got a lot of vegetation. 100% cover, lush growing, vibrant, high biomass, like the Amazon or Irish pastures in May. Okay. Very vigorous growth of vegetation. And by looking at the indices, we can see how that growth changes over a season or after an event. The forests there are sort of dark red. They have a lot of vegetation. There's a lot of biomass, but like most middle-aged things, they're just sort of ticking over. They're not very vibrant. Okay. These vivid reds and pinks, this is probably intensively managed grassland agriculture. So how can we use that set of observations to help farmers or to understand the farming environment? Well, one of the easiest ways is to look at Ireland's most important crop, which is grass. And by looking at how grass growth, because normally we don't think of grass as a crop, we don't worry nationally on statistics on the amount of grass that's grown or harvested. We concern ourselves with the national wheat harvest and the barley harvest. But grass supports 15 billion worth of industry in Ireland. It's the fundamental of the Irish agriculture. So it's important we understand it well and we help farmers manage it. And one simple thing we can do is look to see how grass growth this week compares to the average grass growth over the last 10 years. If it's a good spring, the grass will be growing faster, better, earlier, so we can see better growth. If it's a cold spring, the grass growth will have started late, so we'll see a delay, so we can see that the performance is lacking. And this is one service we do. We use a satellite called MODIS, and we, on a weekly basis, we compare current conditions to previous conditions, and we can get this information now over WebGIS, over the internet, and over a phone application. Okay, so the farmer can just see how well conditions are compared to average. And you think, surely the farmer would know. But we have lots of studies to show that farmers don't take very good records. They just rely on rules of thumb. As engineers, you all do the same. But we know as well that people are very poor at recognizing real averages. They respond to the past immediate conditions and not to the long-term average conditions when they're judging their own performance this week. And since we've got climate change, we've got extreme weather conditions, it's very hard to judge, to have a sense of what is normal at the moment. Okay, so this sort of information allows farmers to establish a benchmark of their own performance of farming. We can go one better. One of my students has recently built a machine learning model that takes the satellite data, the individual pixel of a satellite image, and putting it through a machine learning model called a neural network, we're able to estimate the amount of biomass in the field, okay, in terms of kilograms per hectare. So this replicates or replaces the sort of measurement a farmer would make themselves when they walk the field and try and estimate what the yield of their grass is. So we are now in the process of building a national model where we'll say, this week, this is how much grass, how many tons of grass have grown on your farm. Therefore, this is how you plan for the following week's grazing and silage harvesting. We can even get around the problem of clouds. There's a new series of satellites from the European Space Agency called the Sentinel satellites, and two of those are radar satellites. And radar, if you think of the optical satellites as cameras, as eyes on the Earth, the radar systems, they're like ears. They listen for the reflection. They respond, they send out a microwave signal, the microwave signal bounces back, and they measure the intensity of the return. And that microwave signal responds not to colour, but essentially to the electrical properties of the target. So it responds to the moisture content of that field, it responds to the amount of biomass, it even responds to the roughness. It even responds to the cows. Okay, those are those cows there. And we can look and see what the farmer's been doing. This is a paddock arrangement, so farmers crop their fields in paddocks. And these two have been grazed. This one hasn't been grazed. So we can actually look to see what management is going on in the field. So we can see how the grass that's growing is being used. My own personal hobby, I think I could think of this as my hobby project, are hedgerows. Okay. I always think hedgerows are underestimated or undervalued. And we've used some of this satellite technology to map all the hedgerows in the country. So we've seen that if you combine all the hedgerows, if you were to push all the hedgerows together, it occupies a space about the size of County Louth. Okay? So it's a vast amount of tree cover that's not recorded in any sort of inventory. And we can go further. If we use a technique a bit like this laser pointer called LiDAR, which I'm sure some of you are familiar with, we can measure the three-dimensional character of the hedgerow. And from that, we can measure the canopy height, the spot heights, and then invert that volume measure to actual biomass in the hedgerow. So now we can start recording these in the National Carbon Inventory. The other side of the equation is what's going on underground. It's not easy to see underground, okay, especially in Ireland, because it's nearly covered all the time. If you're in somewhere in Saudi Arabia or somewhere with very arid conditions, some of the microwave technologies will see partially a small way underground. You'll get a response from a volume of the soil. But in Ireland's waterlogged soils, it's difficult to see underground. But we have come up with a method where we look to see the response of plants growing early in the spring, and if they're growing well in an area we've mapped as being a poorly drained soil, something's going on, and that something is probably the farmer has put in artificial drains. So we're building up a map of the artificial drainage network for Ireland. Okay. This is important in terms of managing future productivity for agriculture, but again it's important for carbon accounting, because if we start draining more land, that has a negative impact on our carbon sequestration and our carbon accounts. And then we have a couple of drones which we fly, and they have thermal cameras. And by using the thermal cameras in a certain way, we can look underground, and we can see for underground drainage patterns. So this is so we can show show the farmer, are your drains performing well? Where should you put new drains if you're planning to do a drain? Since drains are not static objects, they have to be managed, cleaned, drained. If you put something called a mold drain down, you have to do it again in 5 or 6 years' time. So there's a lot of business around the issue of drainage in farms that's under-recognised and under-supported. So we're trying to improve the technology support to put in new drainage into farmland. The animals and the farmers don't live in isolation. They live in a landscape. They live in a habitat. It can be a good thing. So farming can be associated with high nature value, with particular habitats we want to protect. But it can also be a negative. We can associate intensive farming with excess nutrients, excess cow poo, getting into the water, causing pollution. So we don't have a good handle on where the cows are in the country. We don't have a good data on stocking density and management. But by using the satellites and looking how fields are managed over time, we can make a pretty good model of how many cows are in that field and how much poop they're producing. And we can make a measurement of stocking density. Okay, so this is the first map produced nationally of the stocking density of animals. This is livestock units per hectare. So this is the number of animals in a given hectare. Okay, so it's important in modelling environmental and agricultural production. And then we put a lot of effort into trying to map the land use, the land cover, and the habitats of Ireland. Again, it's important that we have a benchmark for future planning. So this is one point where this might overlap with your worlds in terms of we know that some of the county councils and some of the bodies are using these sort of maps in planning applications and in future zoning applications to try and understand the impact of new buildings, so we can identify crucial habitats, rare habitats, and the range of habitats. And more importantly, I think, we can get the linkages between habitats, so we don't have to view land in isolation. We can get it in its landscape. A more recent project is one of my students looked at radar. You may have seen the big floods there, not last Christmas, the Christmas before, and you may have seen pictures of flood maps produced for the towns and the cities from the emergency response system. They do that once off, and it's for the towns and the cities, and everyone thinks that's great, the towns and the cities are protected. But in fact, most of the flooding occurs in farmland. And just because it's farmland doesn't mean it's not a flood. And what we did was we used the radar system. So when the radar signal comes in, if it's grass, the grass is rough, and it bounces some of the signal back to the satellite. If it's water, the water acts like a mirror, and the signal bounces away from the satellite. So on the radar image, it looks black, no response. So by plotting those black pixels over time, we can show, and these colours here represent volumes of flooded water over this area here. So we're able to show only the extent nationally of all the flooding events, but we can look at their persistence and their effect. And this simple plot here shows you the effect on farm production on the number of times it shows up as flooded. So if it floods and clears within a week, it doesn't have much of an effect. But as you see, if you have persistent water over a period of 3 or 4 weeks, then it has long-term impacts for that season's productivity, both in terms of suppressing the plant growth and the grass growth, but it also means the farmer can't put animals out on the field. So even if there's no visible water, they're still so sodden, the animals can't go out. So we can monitor the long-term impacts of flooding. And when engineers and planners say, oh, we'll solve the urban flooding problem by putting floodplains further upstream, we say, well, just bear in mind that just because it's upstream and it's not a city doesn't mean it's not a flood. So that's me finished. A very quick overview of how we use Earth observation to help farmers. So I'm looking down at the gutter. From now on, the rest of the speakers will be looking from the gutter up into the stars. If you want to be your own spy agency, you can get all this data, billions of dollars of free data, essentially, and free infrastructure. If you just Google ESA Sci-Hub, that's the European Space Agency, the USGS Earth Explorer, or Landsat Look Viewer, they give you all the data. So you can go into any of those and you can get an image of Clyde Road today, okay, taken today. Okay. And if you do need to go any further, you can get specialist software to help you. There's a big list of, there's lots of free software. Okay, thanks for your attention.
Thank you very much, Stuart. Very interesting. I suppose anyone who knows what we do I heard you saying benchmarking. we'd be very big on benchmarking. So benchmarking of landscapes is something that we'd be looking to see how you do that. But I have to say that how you actually go about communicating that to the farmers, we might catch that in the Q&A session later on. And thank you very much. So we're going to move on to the next speaker. You're going to set up your computer, fair play, Niamh. So the next speaker is Niamh Shaw, and we're going to move on to a Mac. Our next three speakers are very much on the Mac variety. So if anyone who's webcasting in, that's the reason why the screenshot is on the wide angle rather than just of the screen and the speaker. So Niamh, I saw Niamh speak first at a Science Foundation Ireland event with Dava Green, and I have to say she blew me away with the way she was able to communicate and her enthusiasm for space. Niamh is an Irish engineer, a scientist and a performer. She's passionate about all things space. I think that's fair to say.
Thanks very much. Applause there. Fair play.
We weren't able to get her here for our last event because she was often launching a satellite, as far as I can remember the last time, in the European Space Agency.
Oh yeah, that's right. Single-handedly.
She was there pressing the button, I believe. And she's been most recently out in the Utah desert simulating a space mission.
Yep.
So look, without further ado, Niamh, I'm going to hand it over to you.
Thanks,
right?
Conal. Thanks very much. Yeah. Thank you. And actually, that was the launch of the Sentinel B, that you're using. So it's great, Stuart. Fair play to you. Fair play to you. I did that single-handedly, just in a day. But that was the launch of that in Darmstadt in Germany. Thanks very much, Conal and Frank and Tricia, for making this happen from Cooney Architects. My name is Niamh. I have a background in engineering and science. And I came from a very creative family, which sounds great, but it's actually quite confusing. So most of my life, I've kind of not known what I really wanted to do with my life, but I just knew that something was missing. But I remembered when I was very young seeing this picture of our beautiful Earth from a distance and thinking about the person behind the camera at the time and wanting to be that person and wanting at some stage in my life to be fortunate enough to get to see that view of the world. I still desperately hope for that to happen. My aspirations have changed and become more realistic, but that's always been very much the forefront of my life's mission. Now, I wasn't actually around when that was taken. It was actually a year before I was born, 1994. Sorry, what? So let me ask you. Let me ask you this question, because what I'm going to share with you is a very personal story, because I really want to bring humanity and people to engineering and science and the space agenda, and use myself as a vehicle for that, because that seems to be the best thing that I can do to contribute to technology. So, have any of you ever had a moment of clarity, like a moment in your life where you suddenly see yourself in a very different way, and you realize in that moment that you have a huge decision to make, and if you don't make it, you will probably regret it for the rest of your life, as you do? No? Okay, well, I had one, okay? And it's kind of scary, but at the same time it's cathartic, and thankfully I was old enough to do something about it. So I'm making this show, it's 2011, and I'm very lucky at this stage. I've stepped away from engineering and science. That's not why I was lucky, it was just that I'm finding my way merging art with science and technology, because that's the kind of world I grew up in as a kid. And I'm making this show, and I'm kind of obsessed with molecules, and I get to go to CERN in Switzerland, where they're smashing particles apart to try to figure out how the Big Bang, how we all got here in the universe. And I'm looking at all these beautiful theories and particle physicists, and I come across one theory, which is string theory, which hasn't yet been proven. It's a beautiful theory which kind of unifies the whole everything in our universe, from the smallest thing to the absolute largest thing. And it has a beautiful philosophy to it, which is what I kind of attach to. And it basically, a string theory is based on, like, all atoms are made of smaller particles which are broken down into subatomic particles, and what if there was one unifying thing that made them all the same? And this theory is that what if it's just like this vibrating string of energy, and depending on how it's ordinated depends on what type of subatomic particle that you get, which becomes a chair or a person or whatever. And the maths of that is quite complex, and the maths of it is such that the particles are so small that they technically and mathematically exist on higher dimensions. And so I'm kind of going to myself, right, well, if I'm made up of atoms and I'm made up of these subatomic particles, then I must be made up of these vibrating strings of energy, which means I must exist on higher dimensions. And so, you know, we exist in a three-dimensional world where we are aware of duration, which is perceived to be this fourth dimension in time. And basically, if we could see ourselves in the fourth dimension, our lives would be like slices off our three-dimensional selves from moment to moment. So you could see the moment of birth right back there and the moment of death right there. And we'd walk around like kind of some sort of undulating worm. And then the fifth dimension would be every time you make a decision, your undulating worm kind of bisects and goes off in a different direction. So you build this kind of tree structure of all of your life choices. And of course, that tree structure is all the way through nature, this beautiful pattern. And so the strings that the physicists were talking about, they exist on the 10th dimension. So if I'm a person and I'm made from atoms and I'm made from strings, now I can look down on myself from the 10th dimension and I can see this tree of life, all these choices, and now I have an opportunity to figure out what am I supposed to do with my life, because something has always been missing. So the show was me looking at all these key moments of my life that I was able to activate through video. So the girl that stayed married, the girl that stayed working in UCC in Cork in food technology, the girl who took that job in New Zealand chopping up fish guts. That was a close shave. The girl who wanted to be a ballerina, the girl who wanted to be a Muppet, I made that one, and the girl who wanted to be an astronaut. So I made videos of all of these, and when I went to make the astronaut one, I contacted the European Space Agency, and they very kindly gave me their spacesuit. And all I could do was just line up a load of science fiction movies. I'll share that with you now. So far, so good. Having a great time, obviously. Loving it. And that was from the $6 Million Man, by the way, just in case you're wondering. But then as it goes on and we continue to video, a very harsh truth starts to kick in. And I'd like to share you this very personal moment because it's really important to me. And I feel in the suit, I feel more sad. It feels very real that I'm not an astronaut. So that was my moment of clarity, folks, you know, and I don't know what to do with that. You know, when you have those kind of moments, like, you can't really ignore them. And if you do, you'll always know that you had that moment of clarity and you did nothing about it. So thankfully, I was at a stage in my life where I was strong enough to do something about it, because I had actually had that thought many times during my life, but I was never brave enough to do anything about it for a number of reasons. One is, you know, the neighbours, what are they going to say? They're going to laugh at me, you know, the usual Irish sneers, whatever. And then the other thing was I couldn't find anyone tangible who was actually doing anything in the space industry at the time. I grew up in the 80s. There were no role models in Ireland for anything to do with space, and the only people that seemed to be able to figure it out were the people that got to go to the Kennedy Space Center, or they visited NASA, or they knew somebody in NASA, and they're the people that I interviewed subsequently at ESA who found their way forward, but I didn't. But thankfully I was at a stage when I was making this show that I had kind of figured out my own personal perception of success. Up until this point, I probably was your classic Irish person, you know, do a good leaving cert, get a good job, go to college, and I did all that and I loved it, but there was always something missing. And so on paper, everyone went, you know, oh, she's very successful, but deep down I knew I wasn't succeeding in myself. So that's why I pursued the arts. And so I had to completely rip up what society's perception of success was and figure out my own, which is what I did, which then gave me the freedom to think bigger and kind of go, I genuinely want to see what happens if I devote the rest of my life to getting to space, just even as an art experiment, as a performance artist for the rest of my life. And that's what I've been doing since 2011. And it began really simply. It just began with conversation after conversation. And one thing I've learned through all this is like it's people everywhere is what makes everything happen. So I reached out to Blackrock Castle Observatory and Claire McSweeney there in Cork, and together we put in an application to Science Foundation Ireland and was making a show. And I went public, and this was 2014 out this decision. I went public, I wrote this article in the Irish Times about I'm going to get to space, you know, like this mental article. But I knew if I made this massive proclamation that I wouldn't fail on myself, I wouldn't bail, you know. And so everybody knew all of a sudden, and I'm sure there were loads of people laughing behind their backs, but what I love about Ireland is nobody tells you that stuff to your face, you know, it's great. We're such a lovely country, aren't we? We're so encouraging of each other. And so I made the show to space, which first premiered during the Fringe Festival in 2014 in Dublin, and then it went to Edinburgh, and it kept going and going and going, and science festivals booked it, which was great. And what actually happened was that show was about me allowing myself wanting to go to space, but I actually hadn't made any efforts in making it happen. It was just like this catalogue of people that I'd met along the way. I'll give you just a wee trailer of it so you can see what it was like. That was the trailer to the show, and as I said, it toured, and what was lovely was something that came out of it that I wasn't expecting was because I was doing something mental, it kind of allowed other people room to consider their own life choices, and so people started contacting me and asking me advice about very interesting things that they wanted to do with their lives that weren't as out there as what I was doing. So that was a really lovely side effect of it. And then the other thing was that people started to want to help me, and so I was told about this program called the Space Studies Program, which I participated in 2015, which is a program run out of Strasbourg, and about 120 people from all over the world who are also space enthusiasts suddenly merge together in a different venue every year. And so I was in Ohio, and it was in association with NASA Glen that particular year. And now I'm in a room with 120 people who all want to go to space. So it's like, it's no longer weird. Now it's normal. So I found my kin, which was great. And the other amazing thing was I'm around people now who are really high achievers, and everything they say they want to do, they make happen. So now I'm around people who are challenging me and pushing me to think bigger and to go bigger and to reach out and seek answers for myself and how I can actually achieve this. And it was a fabulous experience. It really was. And I met people that have really set me on my way to going one step further towards achieving this dream. And I don't know if you realise it, but it was actually the same space studies programme came to Cork this summer, and I was very fortunate to be involved in some of the lecturing on it. And indeed, Guy and Dava were there too, who you'll hear speak in a while. And so up until this point, I hadn't really kind of realised, well, what is it about? I just wanted to get to space. So it's kind of like going to Aeronautics and said, can I get on a train? You know, like I didn't actually have any destination or plan in mind. And so it became more tangible. And by being surrounded by people who were geologists and astrobiologists and people specialising in different areas of science and engineering around the space agenda, they started to educate me. And I presented a paper at the Astronautical Conference in Mexico, and I happened to sit in the room with this gentleman here, which is Elon Musk from SpaceX. And where I hadn't really thought about Mars really before, I had just thought about maybe the International Space Station, this gentleman unveiled his grand plan to colonize Mars, and actually he updated it almost 10 days ago at the next Astronautical Congress just a few weeks ago. And his talk was really interesting, and it was amazing engineering, like, you know, it's just like sexy as for all of us engineers, right, who love our technical stuff, and rocketry and everything was beautiful. But the really interesting thing was there was very little talk about humanity or civilization or society or culture, and I got worried. I got really worried, because I definitely wanted to go, but I went, nobody's talking about, well, what's that going to look like, and how are people going to deal with that, and what's that going to be like in your body, and how are you going to make that 7-month journey, and what are we going to live in, and what are we going to eat, and so I became really interested in that. And at the same time, from the Space Studies programme, some of my colleagues invited me as an artist to participate in a scientific and experimental study in one of the analogue research stations around Ireland, or not around Ireland, I mean around the rest of the world. So there are different research stations around the world that focus on particular aspects of future space research. And one of them is the Mars Desert Research Station, which is in Utah, which is in the middle of the desert. And it allows people, anyone from an academic background, or, you know, or science or technology or artist background, to make an application to conduct genuine science when you're there. We put in a very intense application and we got it, and suddenly now I'm part of Crew 173, which is a simulated Mars mission in the Utah desert. And actually, when I was speaking at your event, Frank, I was just about to go, which I think was last November or something. So now I'm back to tell you how I got on. So this is it here. It's the most beautiful part of the world, and it really is in the middle of nowhere. And that white building there is the actual habitat, or HAB as they call it. And it's run by the Mars Society. So I was there for 2 weeks with a crew. This was them here. To the right is Roy from Israel, a geologist, and then to his left is Michaela from Slovakia, an astrobiologist. Behind Michaela, the big tall guy, is Rick from Australia, an astrobiologist, and then beside him we have Idris, the engineer and entrepreneur, and then myself. And I was there as the artist to sort of capture the whole experience, because now I realise now that my skills in being an artist and a scientist and an engineer, I can start trying to explain to people what it feels like in kind of an everyday language, and be able to translate the science and engineering in my head and put it out in a human way on the other side. And so we were there. We were from all over the world, which was a lovely element to it, and we were all alumni of the Space Studies programme. I mean, 4 of us were from the same year, and then Rick from Australia was from the year below. For those of us who love schematics, God knows we engineers, we love a good plan. So this is the layout of the habitat. The larger circle is the ground floor, and then the upper deck is the smaller one. And that gives you an idea of the layout of it. It's 8 meters in diameter. Downstairs is all about engineering, and it's about suiting up and going in and going out of the habitat. And then upstairs are your living quarters. So you decide how much of the sim or the simulation you want to invest in. So we decided we'd go full sim, which means every time we go outside, we suit up as if we're on Mars. Mars, of course, has an atmosphere very rich in carbon dioxide. It also has a gravity 1/3 that of Earth's. We couldn't simulate that, obviously, but we did everything we possibly could. And we also lived as if we were isolated. We didn't have any interaction with the outside world, bar very limited internet, where we would communicate with Mission Control and Capcom, which is the actual person dedicated to talking to astronauts when they're on a mission, for 2 hours a night. And then we ate their food. So I have some videos which I will show you about what that life looks like. So here is me pretending to walk for the camera towards the habitat, or the HAB. And the greenhouse sort of is, you know, it's called a greenhouse, but it is actually a greenhouse. But it simulates the actual area where you would grow plants, and that's what we use for our experiments we had 2 main experiments, which I'll explain in a minute. So you would always go out the airlock and come in, and it was like 2 doors. So you'd go in one, you'd have to decompress and then come out the other. And every time you go outside, you'd have to suit up. This is the ground floor, the engineering section here. And I'm just opening the door here. What I loved about the Mars Desert Research Station is everything is kind of broken. You know what I mean? I kind of liked it. Like, it's in need of a serious overhaul. But on Mars, it probably wouldn't be nice and fancy. You know what I mean? It wouldn't be glossy. It would be broken. And I kind of liked that about it. So everything didn't kind of work. It kind of worked to 75%. So you were always fixing stuff. So that's the airlock. And then you just saw to the right are spacesuits. And they were kind of like, it's just to simulate the impact of it. So we had our Navy kind of suits, basically. And then we would have the helmet and then this rucksack to wear. This was the stairs up to the living quarters. I fell down that many times. It's got about, it's less than a 30-degree, definitely. It's like a ladder. It's bizarre. It's bizarre. I don't know why it wasn't just a normal ladder. I think it was just to push you over the edge in the early hours of the morning when you're trying to go to the toilet, which was blocked for most of the time. So this is the living area. You know, it looks normal enough, which was great. That table became the absolute, like, heart and soul of the mission. I actually made a movie about that table when I was there as part of my art piece. And then these are the living quarters here. You're going into my room now. You could also call it a broom cupboard. There was no windows. I just slept on top of that box. And the heating system was like hot air. I'm sure it was very efficient. It was gas. But I was chronically dehydrated for the full 2 weeks I was there. Like, I'd wake up every morning going, I can actually remember it. I'd have a blinding headache, and then you'd go to have a drink of water, but because the water supplies are limited, everyone would go, "Are you having a drink of water, Niamh?" So, you know, you'd have to sneak the water. It was like and then this is the food. This is all freeze-dried. I think the one Michaela's opening, that's freeze-dried egg. You just add water. It was lovely. Thankfully, I have no palate for cooking, so I didn't care less what I was given. But it was freeze-dried cabbage, freeze-dried sausage, freeze-dried raspberries, freeze-dried. You get the idea. And this is the greenhouse. And to be 2 main experiments. One was to grow different plants on Mars or on our habitat, and Rick was involved in that. And Michaela then was also involved in it as an astrobiologist. This is just like a time lapse of every morning. You would get into a routine. You think you have so much time because you've no distractions, but the day just goes like that because everything takes 4 times longer. If you wanted to go outside on an EVA, which is what it's called, an extravehicular activity to suit up, you'd have to ask Capcom. So you plan your day together, you'd have breakfast, and the day would just go. And I was involved in logging everything, so I'd film everyone on their EVAs, people inside, people outside, and you know, just logging cards and stuff, SD cards was amazing. This is a typical. I wanted to show you this. This is a typical suiting up procedure. So there's a GoPro on Rick's head, and so we're suiting up. So you've got this heavy rucksack, and you've got your flight suit, and then you wear the helmet, and you're radioed up. The quickest we could get everybody into suits was like 40 minutes. And then once you put this on, obviously you can't touch your face or whatever. And again, because everything was a little bit sort of broken, it would immediately fog up. You couldn't see that in front of you, which again I kind of liked, because again it would probably be even tougher on Mars, so having a bit of fog is kind of nothing really. And you would always have to stick together because of your limited visibility and the fact that when you're wearing that heavy rucksack, it's very hard to walk around, and I had cameras and I had lens and I had tripods and stuff, so that was pretty difficult. And then in the Science Dome, then another big experiment that was going on was Idris and Roy were trying to design a 3D brick, as if we were to live on Mars, if we could design a modular brick system, what would that look like? And so using regolith or soil from Mars with one chamber and then a second chamber with water on the inside, that would hopefully prevent, would help with radiation leakage and all that. So that's that. So what I learned from that mission was that I was way hardier than I thought I was going to be. I was very worried about the isolation and the fact that I was going to spend that much time with people I didn't know. But I actually did way better than I thought I would do, and I was able to cope with the chronic dehydration and the bad food and the blocked toilet and the fact I didn't shower for a full 2 weeks. I was fine with it. I was perfectly fine with it. So that made me go, okay, I actually have a little bit of the qualities necessary. And then again, more people kind of keep helping me all the way, and a lot of that is that I'm just like leaving myself open to all sorts of opportunities. And then recently in August, basically a team of people hired the parabolic flight in Russia to participate in a weightlessness flight. And as an artist, I was given that. It was still expensive, but I was given it at a kind of a cheaper rate. And so I went with that. And it was very important for me not to just, I feel that if I did that, just a weightlessness flight, it would feel very self-indulgent, and even though I'm not a multimillionaire, it would feel like I was some sort of multimillionaire having this exclusive experience. So it was very important for me to reach out to the general public and ask them what they wanted me to do when I was there. So I did kind of two things. One was I brought this little doll with me, which is a Lottie doll, and I've been working with them. They're a company in Donegal because they very much believe in empowering young girls to be anything they want to be. And so they get children to design their own dolls. So Lottie comes with me everywhere I go. She came with me on my Mars mission as well. And then the second one was there was a young boy who's 8 who has severe autism and ADHD, who's a total space nut. And on Tim Peake's launch day, he spoke for the first time, which was like 2 years ago, and his mum was incredible in bringing him to all sorts of any space-related activities. So he painted me a picture of Mars. It was beautiful. So I had to bring that with me. So I have a video of my adventures in weightlessness, which is just a bit of crack. So this is Hayden's picture, just before I nearly got pummeled to death. I know, right? But it's fantastic. You know, it's I feel very lucky that I had that opportunity to do it. And I got used to it more and more as it was going on. I am really enjoying myself. I laughed all the way. Seemingly I wrecked the documentary that they were making because I wouldn't stop laughing so much. And that's a poster for my show. And then this is the actual, this was a group picture. Yeah? So you can hear me screaming and laughing. And the interesting thing was, I thought the whole experience would be about not throwing up, you know, like that I was going to throw up, and I didn't throw up the whole time. I couldn't believe it. Because lots of people do, lots of people did. They fell by the wayside one by one. Like this guy here on the left, he earned his place there as a prize because he did all these super fit things, and he was pulled out after the second session of 0G, and I managed not to throw up. It was amazing. It's really hard on your body. It really gives you an idea of really how difficult it is as a human being. That's me telling you about the feeling of 2Gs. Yeah. So the reason I did it is I want to know in my body how these things happen. So something as simple as that is incredibly hard on your body, and physically I was exhausted, and you don't know what way is up, and even just to coordinate yourself. So just think for a second about the astronauts up on the International Space Station, and that's where they're just living like that all the time. We take all these things for granted because astronauts are such incredible people. They don't share some of the hardships. So it's very important for me to tell their story and also to share the hardship, which is another reason why I want to do this for myself. So the next phase of what I'm doing is I was very lucky. I got funded again last year by Science Foundation Ireland with Blackrock Castle, and I really wanted to start hanging out with people who work on a daily basis in some capacity in the European Space Agency, and I partnered with the Astronaut Centre in Cologne. So I got to meet people who do everyday jobs, but they all contribute one little bit to the much bigger picture, which ultimately gets the astronaut up into space. So there's hundreds of thousands of people involved in one achievement of getting somebody up on the International Space Station, and I feel it's really important to tell their story as well. So that show actually just premiered last week down in Cork as part of one of the Space Week activities, and again I hope to tour that all over the world. And the reason I do it is I want to tell their story, because I feel if I am fortunate to be a part of getting to space, I think I'll be a minion, and that's okay. I don't have to be the superstar astronaut. It's okay. It means I will have fulfilled what I want to do, and I'll be able to come back and explain in my body what it felt like and how difficult it is. And so I keep pushing, I keep challenging. The next thing I want to do is go on a much longer isolation study. So I'm in very early negotiations with ESA about possibly going down to their Concordia station in the Antarctic. It might take a couple of years, but I have it in my sights. And then ultimately to get to Mars, you know yourself. And, and the very last thing I would say is I would ask you, you know, if you have a moment of clarity, to really take it seriously, and don't bail on yourself if you do have one of those moments, because they really can change your life. And having that moment, while it was difficult, really did change my life, and it really changed my perception of myself in the universe. So in order to, what I mean by that is, like, right now we're in Engineers Ireland in Dublin with an area of 1,200 square kilometres, which is, you know, part of Europe with an area of 10.1 million square kilometres, which is on our planet with an area of 510.1 million square kilometres, and that's part of our solar system. We're 449 million kilometres away from our sun, an insignificant sun, the light of which takes 8 minutes to reach us. And our nearest neighbour is Alpha Centauri, 4.3 light years away, but we are still in Engineers Ireland, and our neighbour is still 4.3 light years away. And we all exist in the Milky Way galaxy, one galaxy of hundreds of other galaxies grouped into local galactic group, which is then grouped in a cluster called the Virgo cluster, which is then grouped into local superclusters, and there are 55 local superclusters within the observable universe, the edge of which is now 46.6 billion light years from us right now, and we're still in the Engineers Ireland building. Thank you very much.
Niamh, thank you very much. It was worth the wait, I have to say. So, David is going to get set up there. Thank you very much, Niamh. I know that I was looking forward to this for a long time, and it was worth the wait. Definitely worth the wait. I know that, I suppose, for what I do in the day job, which is certifying buildings, looking at your ladder there, I don't think it was past parquet, or I do wonder what a regolith building might be doing. How would you actually go about checking that from a building regs perspective? But I'm going to hand you over now to Frank Cooney, who's the Chief Architect and Cooney Architects, and he's going to introduce the next two speakers. And just before I do that, I just want to understand, for Dava and Guy, are you going to do a back-to-back or back-to-back?
Sure,
So you're going to do two introductions
time,
together.
Yeah, let's do two together, sure. Okay.
Just before I introduce Niamh, fantastic, as always. I was just, he stole my punchline, right? I was just saying why architects love this sort of thing, partly because it really messes with these guys' heads. Okay, well, thank you very much, right. Dava Newman, okay, is from Montana, I understand, originally, right? Former athlete, Notre Dame women's basketball, okay, so I'm told, Boston Marathon, national triathlete, and junior Olympic ski racer, okay. Absolutely, right. Dave is also MIT Aeronautics professor and engineer. David goes by the philosophy of love, act, discover, innovate, and is currently fascinated with how to best teach creativity and leadership and the synergies between engineering, design, and art. David, thank you very much. Oh, and I am doing a second introduction, my apologies, right. Guy, my apologies. Born in Argentina, fellow architect, designer, has explored every continent, including Antarctica and the South Pole, where he developed winning concepts for the design of the new South Pole station, okay? Has circumnavigated the planet. He's the first architect working for NASA on lunar bases, Mars vehicles, and a space station. Guy is currently designing and building sustainable eco-resorts and self-sufficient residences in the tropics and other environments.
Hello, everyone. It's a great honor to be here. Thank you for the invitation. Without any further ado, we'll take you on a bit of a tour of the solar system, and so wonderful to talk after the first two speakers. Many of these things were said. There I am doing a one-handed push-ups. Don't recommend that here on Earth, but I've flown thousands of parabolas in microgravity. I design experiments and fly them in space and train astronauts. My specialty is aerospace biomedical engineering, so I've flown on experiments on the space shuttle, 2 years with the Russians on the Mir space station, and now currently have a suit on the International Space Station. And I served as 2 years as NASA's deputy administrator in the Obama administration, which is a great honor. And I resigned in January, and now I'm back at MIT. So if anyone's 26 or, yeah, you can hear me, right? Yeah. Okay, that's too small for them.
Well, this actually, I might need to give you this.
Oh, because I forget, I move around, that's okay. So this is the incredible 3D, this is an incredible 3D image from Hubble Space Telescope. If you're 26 or younger, then Hubble has been exploring your entire lifetimes, searching for answers. Why do we explore? I think it's 3 simple questions. Are we alone? Are there other habitable planets? And is there life elsewhere? And we're getting very close to answering that question. So beautiful image of Hubble, but all of our exploration, we're searching for life. We're don't think we're the only ones. I think we'll find it in the next decade. We've been all throughout the solar system. New Horizons, Pluto. We currently have the Juno mission at Jupiter. Juno, the goddess of Jupiter. Jupiter's pretty rough environment. Talk about extreme isolation. You might want to think about Jupiter. We go in on the Juno spacecraft, we do this incredible North Pole polar orbit, and we zoom right back out. Because the radiation environment in Jupiter is 20 million times harsher than Earth. And lots of great science on Jupiter. Down in the bottom right, I like to highlight that because it's taken by the public, citizen science. This is our largest effort yet to open up all space missions, all 100 of them NASA currently has going on, to the public. Hey public, where do you want to look in Jupiter? The red spot. People love the red spot and the storms. So then we can point the camera there and we take pictures all over Jupiter, wherever the public, because we want to bring everyone into space with us. And maybe in the front you can see what I have superimposed on the red spot. Anybody? Earth. And that's to scale. So our entire planet, spaceship Earth as we call it, fits in one storm, Jupiter's red spot storm. So we are on a very ambitious plan to send humans to Mars. We will get there. We're closer, I always say, to sending humans to Mars than we've ever been. It'll be happening in the next couple decades. A 3-phase plan. International Space Station is first. We've been there already 17 years. Anyone 17 or younger? We've been at universities. Yeah, it's weird. Yeah. So your entire lifetimes, we've had people living in space off the planet for 17 years. So it's pretty remarkable. That's, kind of changes your mindset. Second phase is getting back to the moon, and show you how we're going to do that coming up. And then Mars. Mars kind of looks close. It's really, really, really far away, and it's really hard. So first phase, International Space Station. I asked Scott Kelly on his 1-year mission, hey Scott, what's the technology we should be thinking about? What can I work on to help us get to Mars? And here's what he told me. I think the sound will work.
Yeah, I think the life support systems that we need to keep us alive in space are ideal candidates for demonstrations for our future journey to Mars, as well as spacesuits. We need, I think, new spacesuit technology that requires less maintenance in space, and something that's going to be easier to work in on the surface under the Martian gravity.
So he might know I'm a spacesuit designer, maybe researcher, but life support. What are those technologies I need to be thinking about today to really enable this? And again, funny story from Scott. We usually do 6-month missions to send our astronauts up for 6 months and look at how they're performing, keep them healthy in life. He did a 1-year mission. His new book's coming out next week. You might want to read it. It's going to be great. And but I was at NASA headquarters when I was the deputy administrator, and the phone call came in, and it has 713 area code. Well, that's Houston. That's Johnson Space Center. And so I ignored it because I was in a meeting, and I'll call him back. Well, you really shouldn't ignore it if the last extension is 1,000, because that means it's from Space Station. So I was like, oops. Good thing is he called me back 30 minutes later. David, these suits are really bad. We need your help. I'm all beat up. I had to go out and do an EVA, as Niamh said, an extravehicular activity or spacewalk. So we've been studying astronaut performance for quite some time. Just a few highlights. For our 6-month missions, you're going to lose about 30% muscle mass, 40% muscle strength loss, but that's the good news. You're going to lose 1 to 2% bone mineral density per month. Now who wants to go to the space station for 6 months? Mars is just under 4 years. So, you know, we call these countermeasures, and we're trying to keep people healthy and well. You exercise quite a bit. Don't think we're going to be able to do the, you know, the Werner von Braun and Space Odyssey 2-kilometer craft. So what Guy and I have designed over on the right, that's in my lab, a 2-meter centrifuge. It's kind of like a spin in the gym, if you will. You can sleep if you put that windshield on. Graduate students are tired, of course, you know. And then these are my undergraduate students. Well, I guess I'm with one of them because you have to test out everything before, you know, we get human use approval. But now there's 2 of us. So maybe we'll ride our way to Mars, because we're exercising so that we can basically pull 1G, get 1 body weight loading at our feet. And then this is Guy's design for 4 people, you know, in an artificial gravity sleeping station. Again, so we can think about, that's an ultimate countermeasure, if you will, to help with this, you know, musculoskeletal loss that we see. Well, I promised you to tell you how we're going to get back to the moon. So coming to you next year is what we call the Space Launch System, our heavy lift launch that the world has not had for 40 years. It's been a long dry spell since we've been on the moon, but we're really excited to get back. And so the first mission will go in, now it's early 2019, and with people probably 2021. That's just to wake you up. So it's pretty amazing. Boeing's making the SLS. Orion is made by Lockheed, but let me talk over some of this nice music. We're investing in 1,000 companies in the United States to make this happen. So companies from every state in the US are involved in this. Those are real engines, modified shuttle engines that'll power it. Those are the real solid rockets being tested. A lot of firepower. It says more powerful than Saturn V. That's all hardware. All the 5 cone stages are now built, delivered. This is the Orion capsule that the astronauts will go in. That's been delivered to our Kennedy Space Center. That's animation. That's real. And I'd like to reiterate what Niamh said. It's all about the people. You know, it's all about the people making this happen, working together, because we all have the dream, and you know, we think every dream can come true. This is tough. Entry, descent, and landing. We don't know how to do that for a human mission to Mars. It's a really important technology, so we're testing it out. We're engineers, so we test and we break and test. And you know, we want every system to be really finely tuned so we can accomplish these missions. Lots of thermal imaging cameras on board and a lot of sensors. LiDARs, you name it. So that's it's kind of a tribute celebration to what's coming next for spaceflight. Again, what we call this kind of second phase, if you will. But Mars, I'm all about getting people to Mars. So I want to show you the last 50 years of what we've accomplished in this short little video of our rovers and our probes and our orbiters. You can raise your hand when you're born. It's the audience participation time. I've been thinking about this my whole life. Landing on Mars is tricky, so we try every which way we can possibly try. Again, it's all about the people and the success of when we really nail those landings and when we discover, you know, new scientific phenomena. Now, maybe most of you remember Pathfinder from the 90s. Airbags. It looks kind of small by that rock. And there's a lot of praying and hoping, and there's failure as well. 1/3 gravity on Mars. Airbags are kind of nice and bouncy. So we sent MRO, we call that, in 2005. It's still in orbit around Mars, giving us data every day. There's a lot of dust devils on Mars, if you've seen The Martian. That part's true. Retro rocket propulsion. This is really important. It's a really important technology to get down so that we can eventually send people. Works well for our little rovers, which are only 1 to 2 metric tons. This is the most complicated landing we've done yet. The crane. And so Curiosity is alive and well and sending back HD images every day. It's pretty cool. Get to wake up and see what's happened on Mars yesterday. That's my boss, Charlie Bolden. And that was my big boss. This is what's coming next, our big Mars 2020 rover. Oh, it's not there yet. Maven. That's actually Curiosity. This is Maven. Maven is flying. There's Mars 2020. First time we're going to make oxygen on another planet. We're going to split off the carbon. It's the carbon dioxide atmosphere. We're going to split off the carbon. And that's what I'm about. I spend every day thinking about how we will get people to Mars and explore. Why? Just because it'll tell us so much about Spaceship Earth. So my video showed you the successes, but here's truth in advertising, this infographic. There's a lot of failures. Again, it's far away, it's hard. So Soviet Union and the US, we started this a long time ago in the 1960s. Those red X's, squash, we didn't make it. But the green checks, and we started flying by Mars. And then we finally started orbiting it, and now we're landing. So there's 7 assets on Mars today. NASA has 5, the Indian Space Agency has MOM, Mars Observing, and ExoMars, of course, is the most recent addition to orbit. Next time, there'll be a lander for ExoMars. I want to just share a little bit of the scientific results, pretty breakthrough science. We found water on Mars. It's seasonal. We knew there was ice on the poles, the South and North Pole, but now we have water. That's a game changer. When you're looking for life in the universe, we say follow the water. You can't drink this, so it's a very high salinity. It'd kill you. But exciting, we found water. Mars and Earth, 3.5 billion years old each. 4.5 billion years old each. Okay, sister planets. Well, on Earth, we have a global magnetic shield. Life's worked out pretty well for us. On Mars, no global magnetic shield. Mars 3.5 billion years ago was probably warm, wet, and wonderful, we think. Could have had life, and something went terribly wrong. So from our Maven observer now, we know you're literally seeing the solar wind, the solar radiation. Without a global magnetic shield, we're ablating the ions. This is how Mars lost its atmosphere. You literally see the ionization of the Mars atmosphere. Today, we're left with 1% carbon dioxide atmosphere on Mars. Very, very small atmosphere. Let's get to spacesuits and to the moon. These are my Apollo bloopers you might not have seen. That's Jack Schmitt. The only astronaut we sent, the only scientist we sent to the moon in Apollo 17. It was pretty hard for him to do science because the suit was, but he survived. A spacesuit is the world's smallest spacecraft. Amazing engineering feat. This is the current suit right here. Astronaut Katie Coleman in the extravehicular mobility unit. Our current shuttle space station suit is right here. We've been flying it. I love it, but it's injuring the astronauts during training. It's kind of a system an engineering system that's, lived its kind of fielded its lifetime. So we looked to the future for something new. So we invented the biosuit that I'll tell you a little bit about. It's a pretty revolutionary suit design. Instead of a big gas pressurized balloon, now I'm going to shrink wrap you. So that's called mechanical counterpressure. And through the materials and the design, I can apply the pressure directly to your skin. And that's 1/3 of an atmosphere, 30 kilopascals. We're in 1 atmosphere. Feels pretty good to me. So all I have to do is put 1/3 of an atmosphere on you. How do we do that? There's a little bit of the math and engineering there in that simulation. If you drew circles all over your arm and you moved, the circles would turn elliptical. And those are 2 very special red lines, those bisecting red lines right there. From the circle to the ellipse, they pivot, but they do not extend. So I connect the 3-dimensional eigenvector math, and we get something that looks like Spider-Man. But we've been working on it longer than Spider-Man. And so we have mock-ups and prototypes that we're working on. Guy and I work on this project together. Just again, a little bit of the math we won't go into, but the point of this is we're trying to minimize your energy. In the current suit, the gas pressurized suit, you waste about 75% of your energy just to overcome the suit. That's not much left for exploration. So I want to reverse that, put your energy to good use, and we think we can do that through our designs. Minimizing strain, checking the material properties. It's an individual custom suit, so we measure in great detail. It's basically a second skin suit. So here's one of my grad students. We're mapping and coming up, again, with these lines of non-extension. That's a good place to put your electronics. Orthogonal to that, you need a lot of elasticity. Surgeons know this, plastic surgeons know this, but we just kind of invented the math, derived the math to make this patterning of our suit. Okay, moving quickly along. Ocean worlds. Why? Well, Earth is the most important, and I put it right in the middle. But if you're searching for life in the universe, again, we say follow the water. So just in our solar system, these are really good places to go. Our oceans. This is to scale, so I like this chart. Enceladus, maybe you've heard of. It's spewing at us. These are geysers coming out of Enceladus like crazy every day. Chemical constituents, possibly, that the building blocks of life, potentially. Those hydrothermal geysers coming out of Enceladus. It's a moon of Saturn. Europa is a moon of Jupiter. And we went in 2014, we went back in 2016, and that's a heat map. So we're going to do a mission to Europa to fly by. We know it's an ocean world. It has kilometers of ice and then water. Well, what's in that water? Could it potentially have life? In Antarctica, we look under the water, and we were surprised the first time we saw life. And all these places, mostly moons, are great places in our solar system to look for life. But I'll stick with the theme of Earth, and because it's the only one we have. A few more comments to say about that. We saw these are the 20 Earth-observing satellites that we currently have orbiting. You'll see MODIS go by, you'll see Space Station go by, Landsat. We measure ocean temperature, height, soil, moisture, mapping, all these kind of things. It basically gives us the orbital view, eyes on Earth. And so I want to just share just a little bit of the data that I think is important for everyone to see. So average temperature for the last 140 years. Blue is 1 to 2 degrees below Celsius from the average, and yellow and orange are 1 to 2 degrees above the average, 30-year average from 1950 to 1980. So you can raise your hand when you're born. It's audience participation time. Thanks, Guy. You guys are young, really young. So 2016 was the hottest year ever recorded, only surpassing 2015, which broke all the records, surpassing 2014. So the last 12 of 13 months have broken each monthly record. What do you think my prediction is for 2017? What can we do about it? We can change. Carbon dioxide is human-made. It's greenhouse gas trapped in our atmosphere. Yellow and orange is above 400 parts per million. We don't want to be above 400 parts per million. That's why we have the Paris Accord. That's why we have COP21, COP22 coming up. We'll take a look at the Northern Hemisphere from 2014 to 2015. 1 year of carbon dioxide data. And I'll show it to you in 3 dimensions so you can see 5, 10, 15, 20 kilometers up. That's trapped greenhouse gases, hence our rising temperature, hence our rising seas. So the data speaks for itself. Now we have to think about how we spread the scientific fact and what we can do about it as people to heal Spaceship Earth. I'll show you one more simulation here. This is from Greenland. Had the pleasure to fly in our ice bridge aircraft over Greenland, and we fly over Antarctica each year. So here's from the latest mission flying over Greenland. Last year we lost 287 gigatons of ice. Greenland and Antarctica hold 99% of the world's fresh water in ice. If the Greenland ice sheet goes, it's 6 meters of sea rise. Antarctica, which is a picture down here, lost 125 gigatons. So it's pretty urgent. It's pretty radical. Guy and I, Guy designed the South Pole Station design. He's going to show you about that. I had the pleasure to run around the world in 3 seconds on the South Pole and take a look at finally, Guy Portuguese design of South Pole, which is an amazing kind of spaceship down in the bottom of the world. Okay, so it's a beautiful Earth, spaceship Earth to us. We are disciples of Bucky Fuller, and now our work and our life's work is to make the world work for 100% of humanity at the shortest possible time through all of us working together, and no offense and disadvantage to anyone. So we have an Earth Thinks project through our simulations and data and science, seeing how we can educate and inform and then come up with actions of how to heal the Earth. So my last comment is on what I call STEAMed. I've been dedicated to STEM education my entire life. That's what I do as a professor, but I think we got the conversation wrong. We need to always bring in the artists, embrace the artists. The artists tell the stories. They paint the pictures. They paint the pictures of my exoplanets. I know they're there, but I can't see them. And embracing design, the 3D makers, and telling everyone that this is for you, not filtering anyone out. That's how I was taught in engineering. Oh, it's only for the tough guys, Well, I came along, I wanted to do that. So it's about including everyone and being very diverse. And the reason is because that's how we become excellent. If we get everyone at the table and we get everyone's ideas. So my last slide is a shout out to my heroine, Katherine Johnson, who just turned 99 years old. Hopefully you've seen Hidden Figures. Read the book, it's even better. So I end you with this. Still going strong and loves to talk about math and orbits. She helped calculate and get us to the moon. She's a human computer and a genius, and a contribute to the African American women who literally put us on the moon. I'll hand it over to Guy.
All right. Well, that's a hard act to follow between these three great speakers. I'll tell you my little story. I hear that we have some architects and engineers around. So I am kind of the artist in the family. Dava is the scientist, engineer, and I'm very interested in architecture and design. And this intersection is kind of what we live by. This idea that everybody is equal around the table. And these are extraordinary images. I'm so glad that you showed this picture, because this picture was taken in 1968 as the first picture of the Earth as a Earthrise from the surface of the moon, and also has been an inspiration to me. Actually, I met the astronauts that took this picture at MIT not too long ago, and he explained that when he was in the capsule, extended his arm, and the Earth was totally covered behind his thumb. And at that point, he realized that everything he knew, everybody that he knew, everything that served him in his life came from this little blue bubble that far away. And at that point had this amazing emotional feel that how small we are and how critical it is to really take care of this spaceship, the spaceship Earth. The other graphic is a painting by George O'Keeffe that paints the ladder to the moon, and this is just to show how important, and it's emotional issue of humans looking at the sky, and how long has this dream been alive, even from maybe the cavemen that were really every night looking at the stars. That's why there were gods of the sun and gods of the moon. So this is kind of a genetic thing that we have inside of us that drives us to space. That's why we have people like Niamh that wants to be an astronaut. And the news is good. We are on Spaceship Earth, and we are astronauts. We're all traveling through that universe you described, so we are all in Spaceship Earth. So a little bit about my career. I came to the United States actually, and people ask me, how did you get into space architecture? And I always say it's just by luck. I really had no intent to be a space architect. I'm like the fourth generation architect in our family. My daughter is an architect, but I just happened to land in Houston, Texas in 1969, 2 months before the first landing on the moon. And the university was about 30 miles away from the Johnson Space Center. So, you know, just like me, I went down there and started knocking on the door until some opened. As a graduate student, I was focused on the lunar and designing lunar bases. This is the time where we were on the moon. When I was graduating as a thesis, I asked my professors if I could work on a lunar base, and everybody said, "You're mad, you cannot do it." I asked my colleagues, students, what do you think of designing a lunar base for the thesis project? And everybody says, you never get a job. And, you know, so I called my father, the architect, and I said, you better not do that. So obviously, I found someone at NASA that was excited about this, of having an architect kind of design this lunar base, and found a professor that actually said, well, I can't teach you anything, but I'll sign the paperwork. So it happened that the design of a lunar base really changed my life completely. I mean, I turned a 90-degree from my career. I never went back to Argentina to run the business that I was supposed to run. I got 100% involved in space, and you know, actually met Dava because of that. Because the university that you went to, International Space University, Dava is one of the founders of that university, one of the first students at MIT that created that university that is in Strasbourg today, and she hired me. She hired me to run the Department of Space Architecture, and I'm still doing a good job. I haven't been fired yet, so it's pretty good. And then, and that took me to the Antarctic, to where you know, we were lucky to win the competition for the South Pole Station, and where we did the master plan and some of the technology that went into the buildings up down there. But you know, and ways of, you know, eventually maybe we can do it as an analog to a lunar base and do studies on the South Pole that simulate very much the idea of living on Mars or Moon. And then again, flew with Dava as a subject many times, testing some of her experiments and you know, trying to get me sick and flying, and many times again on that beautiful spacecraft. So, a little side note on our circumnavigation. This is our personal trip as astronauts, our own isolation environment. We lived 1.5 years on this 47-foot boat, crossed every ocean on our own, just the two of us. So every day, you know, we kept this kind of space presence to everything that we did, very much like you did in the simulator. However, we were in this absolutely beautiful environment. And the most important thing, again, of this whole thing at the end of the day was really meeting amazing people that thought and perceived life from a very different perspective than us, and learning from that and really changing, you know, our life. And so truly we call, we have a division in our life that is, you know, BC and ACs, before circumnavigation and after circumnavigation. We really made some changes in our lives when we returned from this amazing journey. So this is what we saw most of the time. So this is really like the ocean is like a desert. You know, we just like the surface of the water, and every day looking at the stars, every evening, you know, just we always got together for the sunset. Even though we were on duty 3 hours on and off, we slept only 3 hours, and then 3 hours on and off every night when we were on sea. Dava explained a little bit of this, but I wanted to remind you that we are here right now working on the space station, looking at low Earth orbit. We're planning to go around the moon and then eventually to Mars. And I had the honor really to work on the space station, a tremendous amount of work, over a decade worth of my life, 100% focused on humans living within these modules. These modules, and the way this was designed, and this is actually part of my master's thesis, was to figure out how do we build a massive space station from one module up. So it's not like building a huge foundation and then building smaller modules. It's the other way around. It's building the little branch on the tree and getting to the trunk. We spend, mostly we were in charge of the habitation module, really thinking about how humans live without gravity and in an extreme environment of isolation. We were designing how we ate in space, how we went to the bathroom, how we sleep, how we interact, and how we work together, and create an environment that it was healthy and productive, so you didn't kind of lose it mentally. So one of the greatest spots in the whole space station is this area right here, is a cupola that is at the bottom of the space station that is pointing towards the Earth. This is the place where astronauts hang out when they're not working. This is what stimulates them really to be there, the ability to look out the window, just the window, and seeing this amazing planet, our mother going by and looking at storms and weather and land and the oceans and the cloud patterns. So these are the vehicles that supply the space station. This one is the one that supplies the astronauts. This is how astronauts go to the space station and come back. It's launched from Russia, and it's a Russian vehicle. And then the series of other ones that actually bring food. It's constantly maintained by shipping food and parts and experiments and so on. And there's a tremendous amount of interface. It's almost every 2-3 months there's a launch to supply the spaceship. This is part of our initial design on the galley, how people eat in space. So we actually went from the design work with people that were actually doing the recipes to how to package it, how to store it, how to freeze it, how to cook it, the whole process. So we built kind of an operating prototype of the galley, designing anywhere from the hydration unit, how do you hydrate food, then how do you cook it. We did a microwave oven, injection heated. There's no there's no gravity here, so there's no convection. So we actually, injecting many. This is happening in the 80s, early 80s, and many of the ovens that we have today in convection happened from the design and the invention of these very high circulation hot air ovens that we have today. There's a freezer and refrigerators and the same issues there. The great thing about not having gravity is that everything changes. It's kind of fun. So that is part of the joy of being in space. And this is showing. This fellow is just having a little centrifugal force in his cans so the cans wouldn't come out, and start flying around. So you've learned all these tricks, to be able to handle. This is the hydration unit, just getting water, whether it's cold water to do a juice or a drink, or hot water for a soup or a hot meal. So this was a project that we spent a tremendous amount of time thinking about, because we were doing it before the space station, the shuttle was just flying, and then the lessons were learned from Skylab, the original space station in the 1970s that the US flew. This is how table ended up looking like. And so the environment is incredibly messy, and we looked at ways to attach food and other objects to the table. A table loses all meaning in space because there's no gravity. Nothing stays in place. So it's really kind of a restraining system. It's a way to keep things in place. So it's organized for us to reach. The cool thing about this is that these guys are traveling about 28,000 kilometers an hour. So that's how fast they're going every 90 minutes around the Earth, and always in a different orbit, so the view is constantly different. So these guys are eating fresh salad made in space. So we have a little greenhouse where they're growing some greens and veggies, and it is a really important experiment where we're thinking that just like the greenhouse that you had in the desert, the idea is to go to Mars and have grow some of our own food. Both for having fresh food, as well as the psychological benefits of tending to plants and living things, as well as the production of oxygen. So the other great project that we spent a lot of time thinking about is the making of this sleeping quarters. This is the private space. This is the place to get away. This is a little smaller than your room, by the way. But really the idea is that this is the place where you want to get away from everybody. You can close the door and speak to. You have a workstation, and you can speak to your family on Earth. You can read a book. You can really get away from it. And we talked about how can we change colors, and certainly we can't get a bucket of paint and paint the wall different in the way you want it. So we introduced the idea of having fabrics as the ability to do several things. One, change the color, change the feel of it, so you can take your sleeping bag that has a special color. Also the acoustical panels, the acoustical properties of fabrics, to give you that kind of soundproof. The space station is incredibly noisy. There's a lot of motors, fans. It's like truly living inside the machine. And and then ideas for storage. So we came up with this idea that the sleeping bag is just a restraint system, so you can sleep hanging on the wall basically. And then the ability to pull your hands out of the sleeping bag to do work and so on. So it's a great place to hang out. Actually, the astronauts love the sleeping stations, and they think there's a lot of volume, which is fascinating. I ask everybody, what do you think of this? The sleeping quarters. We always thought it was really tight when we were designing these things here on Earth, and going back to our bedrooms. But these guys really enjoy it. They really think that the volume is just plenty of volume for them to be there. So that was a great positive feedback. Back to the moon. This is something we need to do, I think, and we're on our way to go back to, maybe not specifically NASA, but as humanity. And the idea there is actually to build as much as possible with the local materials. Use this regolith that is rich in glass and aluminum, iron, and basalt. So the idea is that we can sinter and melt part of the soil to create slabs, so rovers can go on them without creating dust and damaging, say, solar cells or solar panels. Using this material to cast, just like we would cast or extrude concrete here on Earth, very much the same. So did a lot of studies of the mixing of these materials, using the basalt as the foundation and the structure where we would hang maybe modules that would come from the space station, and the use on top of that of inflatable structures. I was lucky that one of my advisors in my undergraduate thesis was Buckminster Fuller, and really flipped my mind and really flipped my whole career and life being influenced by him. So been very much an advocate of designing inflatable structures here on Earth, but on space, where we as students were promoting for the first time the use of inflatable structures for the space station. And I was lucky enough to look at the launch and seeing the first inflatable structure. The first inflatable module of the space station is up there now for about a year and a half and doing very, very well. And then there's a company, Bigelow, that is planning a hotel in space, so where tourists can go and experience zero gravity and just for a price, and enjoy it within these inflatable structures. So, and lately, my proposal to NASA is through this study that we're doing on rovers. The idea not to build a stable architecture, but a mobile architecture. So we're not anchored by a building where you only could do the search around a perimeter of the space. But the idea is, why not build this? We have the technology to build this really autonomous, almost autonomous robots that we could live in and move through the landscape and explore for materials, minerals that maybe could be used for the benefit of humans. So the concept is to build a couple of these, and they will be guided by some small rovers, what I call scouts, that are truly robotic, that are going forward in front of the vehicle, really to understand the landscape and map it, because I don't think we're going to have Google Maps on the moon anytime soon. So really create our whole navigation and aid to these very large vehicles. They're powered by sun, so they actually operate 14 days out of the month, 14 days of light and 14 days of darkness. And during the dark periods, the vehicles actually sit on the ground. These arms sit on the ground so to reduce the amount of power. And they have on the side an attachment of this accordion type inflatable that would expand and double the size of the interior volume to do research, to really look at all the samples that might have been left outside of the vehicle, bring them in, do some testing, and then in the 14 days of light, continue the travel. This is a look of the interior, or what the interior might look like. The idea here is actually to live is in an open. There's no sleeping quarters. That you might really live within the seats, which is very much like spending, a couple of months in first class in an airliner, which is not very different from what we do. And then this is a project, obviously, that Dava presented. So I've done a lot of the human factors, and this is really a lot of what I do is really human factors engineering, human factor design. Is how do you get in it? How do you get out of it? How does it feel? How do we take care of some of the pain that might be caused in areas of the suit, and so, and the design, the actually aesthetics of the suit. And we work together with a group in Italy to laminate the fabrics to try to achieve this kind of second skin feel. We're working on on the helmet. The helmet is an important issue. The helmet obviously is not mechanical counterpressure. It's not like we're wrapping it like the Invisible Man, it's shrink wrapping the head. It's really just like the existing suits. There's under pressure. However, we're looking at a helmet that it would move with your head, very much like a motorcycle helmet versus the helmets that we have today that you're actually inside the vehicle looking out. And it has very limited visibility, particularly if you want to explore the surface of the moon or Mars. And then we're looking at ways, schematically, to modularize the life support system, very much like diving equipment, rather than one monolithic block as the suits are today. So these are projects that are happening right now. We're looking at NASA's putting a lot of money and funding the new habitats, the new deep space habitats that will go from the Earth to the moon. So the space station is going to be decommissioned around 2025, and right at that time we will have the heavy loft, the heavy lift vehicle, the SLS that Dava showed the video of, to launch these vehicles that eventually could go to the moon and maybe the asteroids. So the idea is to test how humans can live isolated, because the moon, the Earth orbit is not that isolated because we're getting resupplied constantly. So how do we actually live in a small environment for long periods of time before we actually launch anybody to Mars? So really to do a lot of technology testing and human testing actually. So the idea is to eventually go to the orbit of Mars and maybe do a landing there. So part of that and coming will be the design of vehicles to go to Mars. How do we actually go for 3 years into space without resupply? This is the big trick, is that we finally, to go to Mars, we were really on our own, not like we are, again, on 400 miles above the Earth. So, the idea is to maybe land with these. Mostly it would be fuel, and then the concept of having a very large inflatable structure that will serve as a habitat to make it all the way there. So back to the Earth. This is the South Pole Station. It really, I think one of the reasons we actually got this project or won the competition is because the frame of mind of our team was really thinking moon, thinking Mars, thinking really another planet, and it truly is another planet. Building on a glacier that is moving sideways several meters a year and growing about 30 centimeters every season, building up snow. And how do you actually build in that environment? How do you build foundations that are that long and moving, but not moving exactly monolithically? You might have inches or really centimeters difference between column and column. And how do you adjust that as the thing kind of moves on the glacier? So we really have great hopes of using the Antarctic as an analog to space, so we can actually do a lot in these environments, but much cheaper than actually going and doing things on the moon before we go to Mars. And then brings me back to actually the other side of my career, which is actually building on the ground architectural projects. And I like to do work, and I'm doing a lot of work in the Caribbean using local materials. So I call it, a lot of the things that I do are designing from bamboo to titanium. And I love it all. I mean, my career expands industrial design, exhibit design. I've designed movie sets. So it's from science to science fiction, just kind of play, between all these worlds. And so I really enjoy designing romantic spots, in the Caribbean with local people, going to carpentry shops that we set up on site with local woods and thatch roof and figure out different ways of weaving these materials and so on. So the whole life is about design. It's really solving problems and give aesthetic value to, and how important these aesthetics are to us humans, to how we behave in different spaces and different types of architecture. So I won't bore you much with that, but creating these spaces, and these are hotels basically that I have built in the Caribbean. But the neat thing about these things is that I am applying a lot of the principles in terms of saving water, collecting water, building massive cisterns, for the times of drought. Every one of these buildings is heated, or the water is heated by the sun. The landscapes are lit by solar energy, and using some of this applicable technology, to Earth. And I think that's the main reason I think we go to space, in my view, is to learn how do we manage this spaceship. This spaceship is out of control. Dava showed the numbers. If you believe in them, it's time to act. And us as engineers and architects are one of the largest polluters of this planet. It's energy, transportation, and the built environment. We are actually manufacturing things, systems that are not really healthy for the Earth. And we need to really consider the Earth at every day and every decision we make in our design process. Just like survival is to those spaceships, we are again on spaceship Earth, and we need to really learn from all the aspects and all the technologies that are being developed today, and pay the price, and have our clients, convince our clients and be committed to make a dramatic change in the way we design things for the Earth. So, so this sunset, can continue to be, and we can still live, within that little thin atmosphere that we have on spaceship Earth. Thanks.
Thank you very much, Guy. That was very enlightening, I have to say. I always wondered what a space architect did. To be honest, I was looking at it and saying, look, this is pretty special. I'd like the speakers to join us up on the stage. We're going to do a Q&A session. I would also like to say that there will be refreshments afterwards for those who've joined us here today out in Cafe Clyde. So if we can get the speakers to take to the stage on the seats that are set up there, and we're going to set up the microphones. So if you can take one over, would you?
Thank you.
So we'll continue to answer on that. So as far as questions goes, anyone who would like a question, raise your hand and we'll see if we can't get you the mic. John?
Thanks very much, everyone. That was fantastic. Really interesting. I just have a question. You're all very interested in getting to Mars. I think ultimately that's the goal. But there's a lot of talk from private organisations who'd like to do the same thing. They seem to be a bit more cavalier about it. Some of them talking about one-way trips, and there seems to be kind of a very blasé approach to what will happen when they get there. You're talking about this is the one planet we have and how important it is to protect it. These people seem to have, I don't know, maybe there is no rules. You can just go if you can have enough money to go, and you can do whatever you like when you get there. I don't know how you feel about it. That sort of private organisation attitude, cavalier travel to another planet. Thanks.
From my point of view, I think any private endeavor in space is good. So people can do whatever they want and believe in. However, I think space is very hard. It's very hard for anybody to get to space, first of all, and transportation. So there's right now, only really the Russians and the Chinese are able to fly, 3 astronauts to space at a time. So very, very hard. So I think that will put a damper on the idea of having people flying one way. NASA, I don't think will ever do it, and I'll let Dava speak for NASA, but we are at the point where more and more people will fly to space by doing tourism, and I think these things are coming, and they're serious, and we will see that, and I think all of us will see it in our lifetime, where we will see tourism in space.
Yep, so I hope I see Niamh there. We're going to have, hundreds and then thousands of people in low Earth orbit. Thanks for the question about getting to Mars. I believe it is Cavalier too. There's a reason Antarctica is not populated. It's really cold and harsh. Mars is orders of magnitude harder. And so the one-way trip folks, they're not credible. They don't have they don't have the technology knowledge, and they don't have any funding. So I don't think that's going to happen. World governments, we're definitely going to get people to Mars, but it's a round trip. You're really going to miss your family. You are really going to want to come home and eat. And but it's it's in our nature of exploration, and really the scientific value of searching for life. Places I showed you, many places, many planets have lost their atmosphere. Well, we got to get this right. So again, it teaches us about our home planet. That's why we're so desperately looking, and to lift up the human spirit, doing the impossible. We're trying to lift up humanity. Let's do the hardest thing we can possibly do. So we'll get back to the moon first, and then get on to Mars. SpaceX in particular, Elon has big dreams. It was great when I was at NASA. We gave him a lot of money, a couple $1 billion a year to make progress, and he is making progress. But make no doubt about it, that's public funding, it's public-private partnerships, so that the private sector can now be in low Earth orbit. We'd love that to be commercialized. Been trying for a long time. I think it's going to stick this time. It's commercialized low Earth orbit, getting lots of people. If we can get the price down, get the access up, and then let space agencies and governments explore, push out to the moon, push out to Mars. And if there's private folks that have capability, fantastic, because I love 2 or 3 heavy lift launch vehicles in the world, and I think you'll see the SLS, I think you'll see heavy from SpaceX, and keep your eye on Blue Origin. They will definitely have heavy lift launch access. And the Chinese as well are investing in, will be on the moon shortly. I just hope we can all go together.
Thank you very much.
And just one thing, just following on from what Dave and Guy were saying, the terrible thing is that if we actually colonize Mars, it's because we've messed up our own planet. So the great thing about exploration to Mars is hopefully it should be, you know, as a human being, I hope it makes us value this planet more, and that we do things to preserve this planet, so that it will always be, you know, it will always be a representation of the amazing achievements of humans when we work together. But how sad would it be that Mars becomes an option for us to live on because we've wrecked our own planet, you know?
Very good question. Frank, I'm going to pass it over to you.
Guy, you mentioned materials quite a lot. Materials on the moon and extracting materials from the moon and using those to build. And comparing that with a non-carbon building methodology that we might aspire to on Earth. What's your thoughts on that? The comparison between using the natural sort of materials in the Caribbean and on the moon, sort of carbon-based materials.
Well, I think it's always great if you can use local materials, right? So we kind of reduce the carbon footprint by eliminating transportation, for instance. You know, now it's very difficult on the Earth because you know, shipping is cheap. We're buying things from all over the planet, you know, and transporting it in ships and containers. We won't have that on the moon, so we will have to make many of the parts, or most of the parts, where now you will be extruded. It will be much rougher in terms of architecture and detailing and all these things. So the fancy stuff that we do are allowed to do here. But I think here we need to choose materials that we need to be conscious of choosing the materials that have less carbon footprint. Just make a simple decision. When you tell your team we're selecting materials, let's look at that as a part of the equation and learn from that and being able to be clever about how do we do that. So, you know, it doesn't make any sense to import wood to the tropics, right? So we build a lot in that material and not natural woods, I mean ancient woods, but we are actually using new plants, new plantation, you know, so now we're allowed to use teak, for instance. That teak is a very fast-growing plant actually in the Caribbean and in Central America, and you know, so it's something that you can plant and harvest and use. So on the moon, actually, the key to do this is energy. It requires a lot of energy to, just like here on the ground, you know, it takes a lot of energy to get, you know, iron out of and make steel or glass for that matter and so on. So I'm an advocate to, if we are going to colonize, you know, if we're really speaking about colonization, we're going to need massive amount of energy, and whether it's solar energy or maybe some small nuclear reactor that we could take very much like say you know, a submarine type of reactor, so we can actually do some of these things, you know, very you know, in an intensive way. I'm speaking in now if we're taking hundreds of people on the moon. So it is difficult, you know, for humans to live without, you know, having an impact, you know, on the environment. But I think more and more we're learning how to do it. It's just now really focusing on that point and actually taking step by step, just like we're doing now with energy. We have, we use a tremendous amount of energy, electrical energy, but we are being clever. We're smarter with designing new light bulbs, new ways to distribute energy, the new ways to put solar panels on housing or buildings to use them, or to actually produce it and reuse it. These double kind of back and forth metering. So, we're moving in that direction, I think. But I think all I'm saying is that we need to be very, very conscious about that and be convincing, particularly with our clients. As an architect, working with the developers, they want the cheapest, the fastest, and and get it done. With the cheapest or the least amount of investment. So it takes a lot of talking and a lot of educating to our own clients to have them buy into this idea. Some of them have it. I mean, I'm particularly lucky because I do this. A lot of the clients that come to me, they already know my philosophy, but I think it's for all of us to have that philosophy.
Thank you very much, Guy. Very good question, Frank. Up the back, and then.
Sorry, I was just going to have a question there about the spacesuits, the new design. The way there's a couple of things there. So it's there's air pressure in the helmet, and you might have said something about a third of an atmosphere or something in it, and then say you're going through the decompression stage. Does it have to decompress slowly because you're in a suit as opposed to being in a confined space? And joints and stuff like that, does that wrap around the whole joints? Or is there the option of, the way the helmet piece is in a compressed area, if you had like compressed at the joints, because it would be restrictive with the sleeves? And then how much time can you spend in it regarding, say, sweating and stuff like that? All that kind of stuff.
So I think I got all four. So for the helmets, it's gas pressurized, and so you really that connection. Again, we look to some diving bladders and things like that. So connection, because it's a lot of force trying to blow that helmet off your head. So that's a kind of an engineering challenge. I just signed up a new student to help work actually the numbers on that. And then the life support, you need a pressure compensator. Since you have air and you have pressurized helmet, you need a bladder, you need basically a lung compensator for the volume of air you're breathing in and breathing out, with kind of the new design of the life support that Guy showed in the image on your back, kind of portable. But it's a very lightweight system, and you nailed it. The hard part about mechanical counterpressure, since you're providing a third of an atmosphere. It's about 20 kilopascals. 20% is through passive elastic materials, and then the design, and then we get an extra, we need to get another 5 to 10 kilopascals. We use active materials. Currently we're using shape memory alloys to kind of cinch it up. I call it kind of my smart zippers, if you will. You have 20% pressure production, you need 30%, so you kind of cinch up, you get in it, donning and doffing in the spacesuit world, fancy words for getting dressed and taking it off. And so you get in it quickly, then you kind of cinch it up to reach the full pressurization. And elbows, and that's why all those colored maps, those are stress strain curves that I went over pretty quickly. But that's what we model. I need about 30-40% elasticity on my elbow, and I have about 30% compression and strain in my, I can't have my suit jacket wrinkle. I have to make that tight and kind of constant pressure. Did you have one other question in there? Oh, to wear it. So we have mock-ups now, our prototypes. Mechanical counterpressure has been looked at for the last really 30 years, but just 10 minutes at a time, 30. We've gone up to 2 hours. Now, the thing is, when we're in our laboratory, we're at 1 atmosphere. So if I put 30% more, I'm overpressurizing you to 1.3. That's not so comfortable. As soon as you jump into my vacuum chamber, it's like, woohoo, and you get a lot of mobility. But again, our design goals are maximum mobility. We're in order of, we have a lot more flexibility. We're shooting for 20 kilogram, 2040 max, but let's say 20 kilogram suit total. The current suit's 140 kilos. So again, it's pretty comfortable. Definitely planning, you could wear it, 6 hours, maybe 4 hours at a time, makes sense. Come in and have lunch. But yeah, 4 to up to 6 to 8 hours.
Next gentleman here.
Thanks very much. I was intrigued by the title of the session about looking at the gap between engineering, science, arts, and the architecture and the design thing. And I have to say, I come from the dark side of the force. So I spent 30 years being an engineer doing projects, and the companies I worked for were high-tech companies that didn't give a damn about creativity. What they wanted was results. And the reason I made this journey was we started looking at why projects failed, and we realized that there was a really weird connection between the first 10% of any given project and the team that did it. The more they understood the context of the project, hey, presto, surprise, surprise, the better and more successful the projects were. And it had no relation to any process we were currently using. So we started looking at design, and we had design processes, quite technical design processes, but we started using design thinking to see how it would draw things in. And this thing of starting to think about the people as well, and a few of you touched on that, it seemed to have massive impacts. And over the last 10 to 12 years, we've been doing it and running programs and all that. I'm just curious, though. I still meet a lot of engineers and quite unfortunately a lot of academics who almost bristle at the idea that the design is somehow important. They almost seem to have this thing that the technical capability is the only thing that matters and who it's for is completely irrelevant. So if you have any tips or hints on, perhaps not using a high-powered Armalite or anything like that, I could actually persuade some of these people. Like we're running a program at the moment with 300 undergrads and 30 master students, and we do a 12-week design thinking program where we help them get it through, and they get it. There's no problem with that. How have you, any tips and hints on how to persuade people to think about the people aspects of what they're doing?
Well, quick comment from being an engineering professor. I mean, it's again, my hope is with the young folks that I teach as well. I'm not going to change anyone over 50. I've already given up on that. But
oh, thanks.
No, but you're a designer, and it's good. Kind of thinks like an engineer now, and I even got some aesthetic talents, from him. So it's a good thing to live with a designer. But no, it's we have to change our curriculum. Change in academia, but we have to do cross-discipline. We have to see the value of it. Again, as soon as we raise up the value, I think that why engineers or scientists bristle. It's just insecurity, lack of knowledge. So, let's educate each other if you really want to be, as good as you can be. And there's a lot of examples, If you want to make money, look at Apple. Look at all the engineering firms buying up the design firms. I don't want to make money. We want to save the earth. So how are we going to do that? Well, all I know is to get, a whole bunch of people that don't think like me around the table to help us think about solving some of these issues and problems. But I think we can do a lot in curriculum design and giving students bringing students at the table. Like, we're all too old here. This little guy, he's the one that's going to give me the best ideas for sure.
Yeah.
I think it's definitely happening. I'm sorry.
No, go ahead.
Please
comment. Okay, you guys fight over.
So, no, I think it's happening in the education world. I mean, more and more we're teaching, this kind of design thinking and beyond. Really, the idea of bringing more people to the team, to the design team. And in many ways, I think architects are ahead of the game of that world because we always have done that. We are the designers, the creators of an image, an idea, a space, and we depend on all these different engineers and designers, interior designers, materials, and so on. We need to look at it that way. When I think about design thinking, it's really designing like it's thinking like an architect in many ways. It's this kind of the studio, feel, and I think that's a great contribution, to the engineering world. And tell me about it. I mean, I was an architect, the only architect working for many years in NASA, and just to be heard, you just have to do it by show and testing and showing them, how. Right. Yeah, exactly. Yeah. So, but the sole designer, the sole prima donna, designer is gone. I think is really about teamwork. Really understanding all the issues, the social, the behavior, and I think that's the great success of Apple. With this exquisite design that is really thinking about the user. So, I think we're seeing some very positive changes.
Just a sort of very down-to-earth example. In Teagasc, we have a collection of scientists, educationalists, and advisors. And our mission is supposed to translate science into action, into performance for farmers. But it is difficult. And when we're designing projects, we design projects as scientists. And we don't think of the end result going to the farmer. And then we try and bring the farmer in, and we say things like, we talk to the farmer. Okay, and that's one stage, but then you have to start listening to the farmer and building it back in. So you bring in the people before even the project is designed, then you can start building their inputs. And it is important to listen to the people, the problems. We can't have this sort of build it and they will come mentality anymore. We have to ask them what they want, really.
Yeah, I think for with the project management society's hat on, I suppose the stakeholder management has to come into it, and we as engineers and architects, and trying to make it work. If you're not considering who you're actually building it for and their perspective on the world, it's going to make it very difficult for you to actually get it across the line.
I'll just say quickly, because we've all said it, I guess I lived my life thinking I could only be one thing, which was why I had my little moment of clarity. I think we are many things at the same time. And sometimes just with the education system in Ireland, we're kind of tunnelled to be like, you're an engineer, you're a scientist, you're an artistic person, you're this. I think we are many things at the same time. And I think if we start getting more comfortable with that multiple identity, I think that changing the system long term hopefully will become more natural. And yeah, having courses where you can have a number of different subjects that aren't necessarily all technical, I think is a very important step forward for our future third level education.
Sorry, can I just add one other thing? And it's something that it's a bit of a bête noire for us in Teagasc and wider, is that we ignore social sciences and social scientists when we're building projects and designs. And we found it hugely beneficial to bring social scientists into the very start of projects and build a project with them, rather than just maybe adding on a social science component at the end. But to build social sciences into design and engineering and science is a big step forward.
One of our youngest members, I see some others up in the top.
Does the moon have any patterns of day and night, or does it vary?
Does it have a day and night?
Does it have any pattern of it, the hours of the days and nights?
Yeah, actually the day lasts 14 Earth days.
Oh.
So for we have 24 hours, right? Where say, in the equator you have 6 hours, or 12 hours of darkness and 12 hours of daylight. And on the moon you have about 14 days of light, so of days, and 14 days of darkness. But that doesn't mean that we will stay awake for 14 days, right? So we still are humans there. So within those 14 days of light, we will have 8 hours at least of sleep, and then the rest of work. And so astronauts follow the exact pattern of the Earth. So astronauts work in the space station with 24 hours. So they sleep the 8 hours. At the same time, say the guys in Houston are sleeping the 8 hours. So we keep that rhythm. Even though they're getting on the space station, they're getting a sunrise every 45 minutes, and every 45 minutes they get a sunset. So every 90 minutes they go around the Earth, and day and night, day and night, day and night. So it's really cool.
And during the dark periods, how are the rovers powered?
That's a very good question, and that's why I said that the rovers actually sit down. These legs would just release the stress and actually let the module sit on the surface, and then during that time we power it with the batteries that you will be charging during the 14 days of light. And it's very, very cold, so at that time you're very critical in terms of power use. It's very much like when we were sailing on our boat, that during the night we were charging during the day with solar power, and then at night you use very little power, so you sustain it with the batteries.
Thank you.
So, but batteries are not that great right now. So there's a lot of research being done on battery research and on power storage. This is a very important thing for living in space, And so there's a lot of work at universities and companies on the development of new batteries, and we really need that.
Hi, well done everybody. That was just absolutely amazing. I spend my life trying to influence people, trying to get them to change their perspectives on what it is that they're dealing with. I don't have a huge amount of evidence a lot of the time to get people to change. And when I looked at the information that you present it in terms of the heating of the temperature of the earth, and that's factual, that's data. What is the trick that we're missing in terms of influence? Because you have the technology, you have the skill, you have the intelligence, you have all of that. How can we still not influence people on a global level to show them how catastrophic this is when you've got, I'm not getting into politics, but clearly I met Charles Bolden twice in my life, and he was my hero. And I always felt safe because in that context, because I thought he knows what he's at, he's a safe pair of hands. I'm not so sure now, and I worry about that, but the evidence is just so compelling. What are we all missing out in terms of the trick to influence better, and how do we all take part in that conversation?
So join us. We need everyone. The project we're working on now is really a way to, there's so many good actors out there doing great things to save oceans and Earth. So Earth Thinks, our new project we're thinking, but maybe we just need to connect. We need to connect people. The data from space is overwhelming. It's great use scientifically, but where do we start? I don't know where to start with, quintillion bytes a day of data. So our new project is, we think about curating the data. There's so much data, we just need to bubble up the good pieces. I tried to bubble up a few good snippets, for you tonight. So when people see that, they just get it. So it's about visual representation. That's the education piece. Can we educate people? Can we curate all this data that is open source, open government? And then education will be the easy part probably. Then how do we bring about change? How do we get, you're probably more expert, then how do you really make people change? But we think that, again, the data is compelling. If we can just curate it and share it, and then we really think if you get 1 billion people doing anything, we think collectively we could actually make big progress. So that's the hope, and we remain eternally optimistic.
Yeah, Earthinks is something that we just started this past year, and the idea is we're speaking with IBM, with Watson, this idea of curating and analyzing, massive amount of data. So with this artificial intelligence and all this new ways that we can communicate, data graphically, just very much like these graphics that Dava showed, is how do we transform all this information so it doesn't matter what language you speak, it is obvious to you very, very, very quickly. So what we're doing is basically designing something that you would have on your phone, like an app, or your computer, where you can understand the state of the Earth very, very quickly. So basically we know the diagnosis of the Earth, and now that translates in action where you, or say us as architects, where we could go to sources for new materials, or really this understanding of what choices we make it to where very quickly you can do it, rather than having one of your people do research for 3 weeks on one material. So really getting down to the data. So the idea is to make every citizen and every astronaut here sitting on planet Earth an advocate for the Earth, to really have it present in your mind. So this is the whole purpose of this, is to create Earth advocates. And then the idea is also to speak to the Earth. So we're testing right now some questions that people could ask, very much like, I don't know if any of you have any Alexas at home, where you speak to the computer. It's a fantastic tool. I use it as my new assistant, really. It keeps me going on meetings on time and tells me what the weather is and how to go to places and so on. So this is coming, and so the idea is to use artificial intelligence, and now we're doing this at MIT. We're starting, we have some students working on it, and so you'll hear more about that. We didn't talk about that today, but hopefully we'll come back and give you some news in about a year.
Just to add on that part, to create your main point, to create that intimate relationship with the Earth. We think that maybe that's what's missing, because we haven't figured it out either. We don't have all the solutions, but what is wrong? Why don't we see the data? Why don't we act better just individually? What could I do today just to do something a little better? Because it makes us feel good. You just do a little something, not overwhelming. And so, hey, Earth, how you doing today? David, not good. I have a You know, well, what can I do about that? You know, so that compassionate, kind of intimate conversation, we think possibly then would hopefully, you know, try to help catalyze and bring about some change.
Sorry, can I offer a slightly discordant note to that? As a data scientist who spends most of his time trying to understand carbon accounts and budgets and talk to farmers about carbon accounts and sequestration and reducing emissions, data really is a tiny thing. It really has a small impact. We're talking about human behavior and choices people make. We all do things that are inimical to our personal health and well-being all the time. We know that we shouldn't eat fatty foods, or we should do more exercise, we shouldn't drink, we shouldn't smoke, and yet we do them all. And those are personal things we're doing to ourselves. So how we make that link to what we're doing to the earth, how do we make, you know, excessive carbon emission a bad habit that we want to avoid, that's the really tricky thing. And that doesn't, you know, all the measuring, the earth, Fitbit for the earth sort of thing is great, and it'll nudge a few people, but we really need massive researches and understanding in the social sciences, in behavior, to make people make that connection and make the changes.
Yeah, I mean, as that's what I mean. I've been racking my brains for like the last 2 years. Like, how can I still haven't figured it out. But like from the artistic side of it, we can humanize things and make them accessible. But it just seems already, we haven't yet cracked it, but if we can personalize it or tell a story or make us connect with it. And I think what's wrong is that it's out, to me even, it's there, but it's not here. Why isn't it here? So I need to develop a more intimate relationship with the planet I'm on, and I haven't yet figured out how to do that. But I think a lot of artists are genuinely trying to figure that out, because I think that's the nut to crack. It's like what you're all saying, so I don't know.
You were talking about briefly the carbon dioxide breakdown into oxygen for the Mars mission, and I was just wondering about the efficiency of that device that's on the rover, and obviously they don't produce that much pollution themselves because they're solar powered and it's reusable energy, but those type of technologies being produced for space travel, how would they better suit being adapted for the Earth environment and helping us control something like climate change, which we've basically been ignoring much more than we should be. And while those technologies are great for the advance of space exploration, it's a little bit more urgent that we adapt them for the current Earth situation. And what would your thoughts be on that?
Well, just a quick response. I mean, everything we invest in for space technology, everything I think about. So Elon Musk is actually a great example. Wants to get to Mars, truly wants to get to Mars personally. That's great. Has a lot of government support. That's great. But what's he investing in now? Better battery technology. So this disruption, and electric cars. We need electric cars. We drive a hybrid. It'd be great to have an electric car in the future. And so again, kind of putting your money where your mouth is too. We need that battery technology to the young man here. And so how can we do those things? And solar power. We can look. And the thing is, there's probably a different solution for each country. What's the U.S. going to be? What's the U.S. investment going to be in getting? We need to redo all of electrification. That's serious. So how are we going to do it? Moving from, we got to get off fossil fuels. So probably natural gas as a bridge. How much solar, how much wind, how much nuclear. But each country, I think, is going to answer that differently. But the good thing is that we're moving forward, but it's so urgent. We need to move a little bit faster.
Yeah, I think at the end of the day is speed. How do we actually make this happen? I think it will happen. I think eventually people will believe and act on it. But as I travel around the world, I realize that more and more people are doing it. I mean, they're living this way and acting on it. So it's really our purpose with this Earth Thinks project is really to accelerate that process, learn from each other. It's sort of like, I call it like a graphic Wikipedia where people can upload. When the farmers in South America can upload things that maybe we can learn in the United States, where the American farmers can say, hey, I'm making this and it's not costing me more, or it's more efficient, or it's worth it. Like organic farming is happening more and more on the planet, using different types of fertilizers, and so on. So it is happening. I think we just, we have the problem that we ourselves as humans are reproducing still more and more. So the numbers are increasing, therefore the needs are there to have more and more of all these things to service every one of them and every one of us. And so, you know, change is happening. Now the question is, how can we accelerate this thing? Going back to the statement from Buckminster Fuller that Dava showed, you know, how can we, you know, create kind of instant change? And we're not going to have it instant, but I think we have some tools by communicating globally where governments become less and less important and policy will be driven more and more by the people.
So I'll just add maybe the last thread between the last two, and listening. You mentioned it, and just listening, because indigenous peoples of the world, they know how to take care of the earth. You know, for sure, that's one thing I've learned. They know how to take care of the earth, and then, you know, what happened to us and our materialism and kind of greed and wealth. And so I think we have to go back to roots. And let's go back to basics, and let's listen to kind of the wisest people out there. And, you know, I think a lot of the wisest people have been on the earth for a long, long time and have been caring for the earth and regenerating the earth. And, you know, I think we can find a lot of wisdom, you know, in a lot of wise people out there, but we haven't been listening to them.
That's great. I think
just make sort of one observation that the technology of converting the carbon dioxide to oxygen on the Mars rover, we do this on Earth. It's photosynthesis. That's what plants do. They take carbon dioxide from the air and turn it into oxygen and carbon. So every time we plant a tree, we're stealing NASA's technology. That sort of approach. But I think ultimately one thing we'll do is maybe genetic modification will increase the efficiency of photosynthesis in the plant. So that's one technology that will use that up.
Okay, so we're about to wrap it up. I think this lady over here had one final question. Am I right? No? Yep.
Yeah, sorry, just a quick one, sorry.
No problem at all. But just to say, we will be having refreshments, and we're going to move the conversation into Cafe Clyde. So if you have further questions, the speakers will be joining us inside for finger food and refreshments.
Hi, just two quick questions for Stuart. One of the things that came to mind when you were speaking was actually an episode, I think, of Ballykissangel, where the farmer put some plastic or wooden sheep out in the field because he was told the EU were spying on him. I'm just wondering about data protection and if you've had any issues in that area. The other thing is, you mentioned about drainage and how you were able to look, you know, under the ground in terms of drainage improvements, and I'm wondering how applicable is that to cityscapes and whether that same technology can be used, and also just as regards other utility services, and whether that can be used as a mapping tool.
As opposed to the plastic sheep, I think that's something that the department used to tell farmers, a bit like we used to have the television detector vans to get people to pay their TVA license. You couldn't really count the animals from the technology they had at the time. But data protection is important. I mean, we do remind people there are no laws to stop people flying overhead in space or aircraft or trying to take a photograph. I mean, it's a fundamentally legal thing to do. But data protection is more about just the legality. It's about the legitimacy of what you're doing and whether you should be doing it and how you hold the data. I was at the Ploughing Championship. The Ploughing Championship is a massive thing in Ireland. It's a big agricultural show. Last week, and I was showing drone technology to the farmers. And we got a number of farmers who were saying that they would shoot the drones out the sky with their shotguns because they were worried about the data protection. And it's a legitimate worry. It's not a legitimate response, obviously. But so we do have to be, as people who use this data and publicize this data, we always have to be wary of the idea of privacy. Remember, we always remind ourselves, I always remind our students that privacy is given. Okay, it's not kept. So we give each other privacy, and we give all the people on data we collect privacy. So it's something we do, not something we don't do. As opposed to the drainage, the particular technology probably won't work because the urban area is sealed. But of course, there are new geophysical techniques where we can use ground penetrating radar. We have this crazy idea of using drones for electrical resistance mapping by having the two hoops on either drone and flying in parallel to try and get the depth there, but we'll see if that works. Okay.
Thank you very much. Now we have a small presentation. I have to say, just once again, I think I'd like a round of applause for all of the speakers. Really inspiring stuff that you have to say goes to the heart, and I hope we can make it socially unacceptable not to do the right thing.
Thank you very much. Oh, wonderful. Thank you so much.
Good architecture. Unfortunately, it's the same.
So we have different libraries.
Cooney Architects have passed on an RAI book, which one of their one of your projects is in it, which is great to see. You do great work. To see you with on the project architect side of things. On behalf of IQPT certification, Engineers Ireland, and Cooney Architects, we'd like to thank the speakers very much, and also for all the attendees who have made the event even more interesting with the very interesting Q&A session. So thank you very much, folks. And we're going to go into Cafe Clyde for food and refreshments if you can join us. Thank you very much.